Hello students, in this video we'll discuss the cumulative distribution function of a random variable. If we're given a continuous random variable, x with PDF f of x, we can define a function f capital of x by the formula, the probability that x is less than or equal to x. And we can see that this is also, by definition, the integral from negative infinity up to x of f of t dt. And this is called the cumulative distribution function. And we'll use CDF for short. Now there are some interesting properties of this cumulative distribution function. Let's discuss some of them. So here are some properties of this function f of x. Well, the first property is that f of x is non-decreasing. And we can see that by looking at f prime of x. F prime of x, by the fundamental theorem of calculus, is just going to be f of x, and that's bigger than or equal to 0, and that shows that f is non-decreasing. We can see that if we look at the limit as x goes to negative infinity of f of x, we should get 0, because that would be the integral from negative infinity to negative infinity, and that should be nothing. Likewise, we can see that the limit as x goes to infinity of f of x is going to be equal to 1. Because as I let x go to infinity, this goes to the integral from negative infinity to positive infinity, and that will be equal to 1 by the property of the PDF, that the integral from negative infinity to infinity of f of x dx is equal to 1. And so we can see a typical graph of a CDF looks like this. A typical graph will look something like this. So here's the f of x axis, and here's the x axis. CDFs look like this. Now that's a continuous CDF. There might be jumps in this, but the whole point is that it has to go to 0 as you go to negative infinity and tend to 1 as x goes to positive infinity. And then the last one, which is extremely important for us, is the third property, is that the probability that a is less than x is less than or equal to b is going to be f of b minus f of a. And this also comes from the fact that the function f is right continuous. Which means that if I look at the limit as x goes to a from the right of f of x, that will be f of a. So we can have jumps, so it's possible for CDFs to jump, but CDFs can only jump in the following way. They can do something like this. There can be a hole over there, then the CDF can jump up to this value over here. For example, maybe that was equal to 1 at some particular point a. But as I'm going to a from the right-hand side, I get the actual value, so I'm right continuous. So the filled-in points on the graph of the CDF are always filled in on top, basically. So you're right continuous. So let's see some examples of these CDFs. So here's an example. Let's show that f capital of x, which is e to the x over 1 plus e to the x, is a CDF, and find the corresponding PDF. So what we see is if I look at the limit as x goes to negative infinity of this function f of x, what I see here is I see that the top of this function is going to 0, and the bottom of the function is going to 1, so indeed this is 0. If I look at the limit as x goes to positive infinity of e to the x over 1 plus e to the x. We can easily see by L'Hopital's rule that this will turn into 1. So indeed it satisfies these conditions over here, these limit conditions. And let's compute the derivative of this function and see what we get. So the derivative of this function, f capital, will be equal to the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And we see over here that these terms are going to cancel. So this term over here and this term over here will cancel with this term over here. So those are gone and that's gone. And so what we're left with is we're just left with a function f of x, which we're denoting by f prime of x. And that is equal to, well, just e to the x over 1 plus e to the x quantity squared. And this function over here is going to be the PDF of the random variable x. So if I give you the CDF, you can find the PDF of the random variable by differentiating. If you're given the PDF of the random variable, you can find the CDF by integrating. So there's the fundamental theorem of calculus relationships between the two of them, and it stems from this fact that the derivative of the CDF is the PDF. And this other most important property is that if you want to compute the probability that the random variable is in a particular interval, which is open on the right and closed on the left, it's the difference of the CDF at the right endpoint minus the left endpoint. Thank you very much.